haben wir einen kleinen, aber feinen Technologie-Pitch. Und der kommt von Dr. Tommaso Pregnolato vom Ferdinand-Braun-Institut am Leibniz-Institut für Höchstfrequenztechnik. An dieser Stelle switchen wir jetzt einmal an dieser Veranstaltung ins Englische. Please welcome Dr. Tommaso Pregnolato. The stage is all yours. You got 5 minutes, your microphone, you got the clicker. And please tell us a bit about Enabling Technologies for Photonic Quantum Applications.
Thank you.
Enjoy.
Thanks. So we are at the end of this very nice event, and I take this opportunity then to step a little bit back and give an overview of the Photonic Quantum Platform. We have here the FMD network, and we had already some info from that about from Klaus. Usually when I present the quantum photonic platform, I like to show this picture. It's a little bit old, but as a nice review of what we need, of the ingredients we need for building this type of platform. We start from generation. We need to create light. We need to create particle of light, very simple, like single photons, or something a little bit more complex, like entangled photon states, or cluster states, as they're called. After it is generated, light has to be somewhat manipulated. We need to very simply take the light from one side, from one side of the chip to the other one. So we need, for example, to waveguides to route these photons, or we can take a step up and increase a little bit the complexity. We make some interference. We have, for example, beam splitter, and we use then this higher level complexity for the photons, or we have even more complex devices where we introduce some sort of nonlinearity, which is one of the key ingredients to have gate operations. And then finally, after we do all of this with this light, we need to, of course, read the results of this computation, these operations, and therefore we need some detectors at the end of the chip. If we look at our network, then all of this functionality in some ways are possible. We have seen a lot of posters in the next room. For example, starting from the sources, some of the partners can, for example, design and integrate diode lasers on chips, which combined with some nonlinear elements, they can create entangled photons. Or other partners have, for example, capability to use and build and fabricate color centers in diamond or in other substrate, which can also be deterministic sources of photons, or single photons. In terms of manipulations, again, for routing the photons from one side to the other of the chip, some partners can build MEMS, we saw them yesterday, that can switch, for example, paths inside the chip and route the photons through it, or just simple photonic integrated circuit like waveguides and other simple passive structures. Or again, using color centers and combining with photonic crystal cavity, for example, we can then achieve the nonlinearity that are necessary for the gate operations. And finally, all the knowledge about superconducting material that we heard today, for example, could be very useful for creating detectors that we can integrate on chip as well. The story, of course, doesn't end here. We can move from one chip to a second chip to a third chip and so on and so forth. So we can connect all of these different circuits and increase even more our complexity. To do so, of course, we need then very efficient outcouplers to take the light from one chip to the other. And we can then integrate everything into a package. We can close everything to keep everything safe inside our closed chip. And again, all of this is something that is available in the network of FMD. Once again, we can go one step forward, and once the light is inside a fiber, it likes to travel, so we can actually not connect only chips, but we connect different sites, different machines throughout the network. Now, for the experts in the room, maybe this is a little bit too far in the future to have this sort of large network, but all the capabilities are here. I think that this makes our FMD network already a little bit quantum. Thank you.
Now that was a tight elevator pitch. Thanks a lot.